Okay, welcome back everyone. Let's start. I hope you enjoyed a little bit of relax after the homework. Let's say that this week was left intentionally empty from homework, and we would like to give you the homework, the second homework, at the beginning or either within the weekend or at the beginning of the next week, and to leave you until the end of the course to perform it. And for the third homework, give you a little bit more of time so you can turn it by, let's say, beginning of January, with actually first half of January, with not too much rush. Another point is related to the, let's say, way we will score the homework. As I said from the very beginning, it will not be scored by the ranking in the leaderboard. I mean, there's no point in that. That was not the goal, and you might get the different ranking in the leaderboard depending on what you did and what you choose to investigate. So we decide, well, from the very beginning that we are more interested in you experimenting based on your, I would say, feelings and curiosity, than apply, let's say, just a winning strategy. Based on that, it will take some time to score the homework, because we have to go through them and we have to figure out what you did and what was good and what was bad. In a sense that things that might go bad are usually related to not doing cross-validation for hyperparameter selection or something like that. But beside this, except turning in just a cut and paste of the notebook, everything else should be fine. Okay. I'm starting the recording of today's lecture, and I will start by some question that your colleague mentioned. And first of all, the first question is related to what do they mean, the different weights that are reported in this slide. So I would like to make a colored picture out of that. So basically, within a recurrent neural network, we have weights which go from the current time instant to the hidden layer, and they represent the, let's say, direct connection of the current input on the output. And these are reported with the letter W in my slides. Then the current input affects the memory, beside providing just direct influence. So for instance, we have these weights here that I'm drawing in green. So these weights are those that are dubbed as W here. So we have the weights in this case. Then we have some other weights, which are the weights influencing the current state here from the previous state. Sorry, no, this is not true. I was drawing a wrong one. Lighter. And these are basically the weights from the previous state to the current state. And then we have some weights which affect, let me go back here, the, let's say, the current output directly from the previous output. Now, as I mentioned, these V weights are not always there, so basically they can be skipped. What is relevant here are these weights. Sorry, let me use the right color. Okay, let me use the same color that I use. These weights, which affect the memory from the input, and these weights, which affect the memory from the input. Then you have the yellow weights, which are here, and then you have the orange weight, which are here. Okay, I hope that with this coding, let's say color coding, it's more easy to trace the thing. The weights that come into the play when you unroll the, just a second, when you unroll, let me use this color. When you unroll the network, are those weights which are involved here in the memory, because they appear in all the replicas of the network, which have, so the green and the blue. So when you replicate them, they appear multiple times. Oh, now I see the doubt. Oh, okay, right. So yeah, I think the doubt is because yes, I did cut an error. Okay, now I see your doubt. Thank you very much for pointing out. So these two weights, which are the weights from the input to the memory and the weights from the past memory, are those which are replicated, and so they have to undergo that averaging process. Let me highlight again with a proper color the right weights. So no, I changed for the wrong color. So here we go. So this is the green, and then we have the blue color here. Here we go. And because of this, now I understand the comment of your colleague. This one and this one need to, let's say, average through the unroll. And indeed, there's a cut and paste error here. This should be WB. This should be WB, WB, and WB here. And here we should have, as it is, the VB, VB, and VB. Yeah, okay, so I see your comments. Thank you very much for pointing. As usual, when you write the slides, you don't see this kind of errors. Thank you very much. And then the rest remain unchanged in what I said during this. I'm just double checking that, yeah, it is. The rest remains the same. As you might have noticed, well, you might not have noticed now, but last time you pointed out some comments on the notation as well, and I have already fixed the slides with the proper notation. So the slide, at least my version of the slide, it updated. As soon as I will finish with this set of slides, I will also update with the correction that we just pointed out. Okay, I hope that this clarified my the question you had on the chat about what is V and what happened to WB. Okay. Last time we have seen that a recurrent neural network has a problem which goes under the term of vanishing gradient, and this vanishing gradient issue can be partially solved by the use of rectified linear unit. Why it can be partially solved by rectified linear unit? Because rectified linear unit have a gradient which is either 1 or 0, and so when it is not 0, you are just multiplying 1 through the gradients, and multiplying 1 through the gradients means to keep the vanishing gradient away, because you do not vanish the gradient. However, it is just part of the solution, because you still have multiplication of the weights of the recursion here through the layers, and to avoid vanishing and exploding gradient, Hochreiter and Schmidhuber, they proposed the use of this cell, which is called the circular error carousel, to keep the weight equal to 1, so the weight, the multiplication of the weight equal to 1. The network that they presented goes under the term of long short-term memory, and it's the one that we see in this slide, which is a little bit more complex, because the memory, which is represented by this line, gets cancelled by what is called forget gate, gets some input here, which is weighted by the input gate, and the output here is weighted by the output gate. It must be noticed that the output is fed back into the network, so you have these two input. One is the input X, the other one is the previous output of the network, which is a function of the current state. Now that we have seen all these steps in detail last week, and today I would like to discuss a little bit more what kind of computational graphs you can build by having multiple long short-term memories together. We have seen already one hierarchical structure. One is this, so you have 2 or even more, 3 layers of long short-term memories. Each of them is embedding a representation of the state. Hopefully, the inner layer, they represent, let's say, a high frequency in the short-term state elements. The second level is a higher level of these, and if you want to put more, you get even more higher level representation of a time series. Here I put 2. Usually you don't put as many in a network, but that's one option that you could do. We discussed about the fact that if you want to process samples from a time series or from a sequence which come one after the other, this structure that you see here, this structure that you see here is the right one. But sometimes you get the entire sequence, and you have to propose an outcome which is based on the entire sequence. Let's make an example. Let's assume you get a tweet, and you want to discuss whether this is a positive comment or a negative comment. So whether it is a positive tweet or a negative tweet. Because of this, what you could do is to process the sequence left to right, then right to left, that you let's say stack together the 2 states, and then you make your decision or regression or whatever processing you want to do based on this stacked representation. So this is the idea of the use of what they're called bidirectional LSTM. Bidirectional because let's assume you have a sequence x0, x1, x2, xt, and you get the same sequence xt, x1, x0, so in the backward direction. At some point you can stack the representation of the x0 sample at the beginning when you start from there, when you come back from the end, and then you base your decision based on this stacked representation, which is the forward reading part and the backward reading part. Okay, that's where more or less we left last time. I also discussed the idea of initialization, because when you start using a network, what you do, you take this network and you start giving this network inputs. But as the first output and the memory itself depends on the previous value of the memory, you would like to initialize the memory, and you would like to initialize also the previous output of the network, because you have this as input from the very beginning. One possible idea is to initialize everything as 0. That's one possible option. Another possible idea is to learn, again via backpropagation, what should be the initial value and what should be the initial previous output of the network. How you do that? We can see it on the right, on the left. Sorry, you have the input, and you backpropagate back here to what is the. Let me write it here. What is the just a second here. You need the value of the memory and the value of age at time 0. So you have these two. Then you know that the state gets propagated through the LSTM, and while the output of the network, which is basically coming here, gets here as well, because we have also a second input, which is that one. Okay, that was everything from last time. I left you last time with this plot. This plot represents the different architectures you could build with a recurrent neural network. So the first one that you see here has some input, has some hidden state, let's call it to it, a hidden representation, and then you have an output which is based on the hidden representation. This is a static network in the sense that you get one input, you get the hidden representation corresponding to that input, and then you get the output corresponding to the hidden representation of that input. Sometimes this hidden representation is also called latent state, because it is one hidden state of the network which generates the output. Now, in the fixed size input and fixed size output, you don't have memory, not at all, because you don't have any recurrency. This is the example, for instance, of the image classification that I was showing to you during the homework, because you get one image as an input, one class as an output, and then you have a hidden representation which is represented by the convolutional filters. Okay. What about time or sequence? Let's assume that you give an image, and this image is used to condition the output of let's say, long short-term memory. An example of use of this is the captioning system. And very similar, you have on the right, you have a sequence of input which generate a single output. And then you have more classical sequence-to-sequence examples. Let's try to see them one after the other, just to give you a few examples on how you could combine, for instance, the sequential block, which is implemented via the long short-term memory, and a more traditional visual embedding block, which could be implemented by a convolutional neural network. So basically, let's assume that we have as input an image. This goes through most likely a convolutional neural network, which will give you a vector, which is this red arrow here, a vector which represents the input. Then you have a long short-term memory here that will start outputting words. Words that might describe, for instance, the scene in the picture. So, for instance, you show the first picture and the network starts writing a person riding a motorcycle on a dirt road. Or for the one on the bottom right, where you input this image, and the network will provide you as a sentence two hockey players are fighting over the puck. So this is a typical example when you have a forcing input, which is, or a conditioning input. You can use the term you prefer, and you generate a sequence out of this embedding, which is the representation of the forcing input. Why do we need the recurrence in this case? Well, it's needed because, for instance, once you have said two, you don't want to repeat two. But the features have not changed. So basically, if you give the same sentence, the network will give you again two. What you want to do is to have a network that says, oh, I have already said two. So the next most likely word given this image should be okay, and maybe players, and so on and so forth. So that's the way you can combining a forcing input, which doesn't have to be an image, by the way. It can be anything which is constant during the, let's say, production of a sentence. Questions? Everything clear? Okay, so far so good. Let's have another example. It's oh, sorry. Sorry, I went too far to the end. Let me discard this. Let me go back here. Okay, let's discuss another example. This is another classical example where as a input you have a sequence, and as an output you have a single value. So for instance, you have a sequence of words like I don't really enjoy the camera of my phone, and the output is the mood of the sequence. You can either represent the mood as a binary variable, so you classify it as positive or negative, or you can have a more graceful scale. So based on this scale, you can do a progression work, and what you do is to predict the value of the output given the sequence. Now, one thing that I stressed last time is that you can think about this sequence of activations of a long short-term memory as a sort of building a machine which is building an internal representation. Indeed, the state of the last here, of the last hidden state, sorry for the pun, so the state of the last long short-term memory will depend on the sequence of input. So it will depend on the specific sentence which has been used for input. So the state, in a sense of this long short-term memory at the end of the sequence represent, let's say, is a representation of the entire sentence. And thanks to this representation, which most likely is related to the semantics of the sentence, you should be able to classify the sentence as positive or negative in a binary case of sentiment analysis, for instance. Finally, models which are somehow classical as well, which use sequences, are sequences to sequences models. They go under the name of sequence to sequence model. And what you try to do is to map an input sequence, like the red one, into another sequence, like the blue one. Let's make some examples. Translation. So you have a sentence in Italian and you want to translate in English. That's an example of a sequence-to-sequence translation. And conceptually, what you could think here is to have an embedding here, an embedding of the input sequence, and then a generation of the output sequence based on that initial embedding. So that's the idea of sequence to sequence in this way. So when you first encode the input and then you start to generate the output. Another task which is a sequence to sequence is a more classical one, where you have a direct map with the output, and what you are trying to do is to learn a function which relate the input to the output. This function is time dependent. What does it mean? It means that if you change the order of the input, then also the order of the output will change, but in a totally different way. So it means that every swap of these two will affect all the resulting toolchain. And this model is nowadays used mostly for translation. While the previous one is also used for question answering, because you can imagine that the red sequence is the question, then you have in the hidden node what is the concept, the request made by the question, and then based on this concept of a question, you start generating text, which is the answer to the question. These are, let's say, some classical examples in recurrent neural networks and long short-term memories literature. Questions? Doubts? Everything is clear so far? Okay. This model, the first one, is called in the literature as seek-to-seek model. So when I discuss the seek-to-seek model, I discuss a model where you encode a sentence, the first sentence, and then based on that encode, you generate another sentence. This is for machine translation, this is for question answering, and so on. So basically, you have an input, which is a sequence. For instance, in this case, the sequence is A, B, C, and you have an output, which is another sequence. For instance, it's W, X, Y, Z, and that's it. So you have a special symbol which says when you should stop generating symbols. At training time, what you do is you have the input, then you have a special character which says from now on I will generate text, and then you generate what is the most likely word or symbol given the sequence of symbols which come before it. And then, or now you know which symbol is this, you use it as an input, and again now your sequence is extended, and you want to predict because you know already what is the symbol that you have predicted first, you want to predict what is the most likely symbol to call for second. And this way until the end. So when you as answer between ABC and WXZYZ, you predict as next most likely letter after the Z as the end of the sequence. At the training time, as you can see, you have this, you have this, and you have this as well. Now, what happens at testing time or at inference time? At inference time, you get your input sentence. So you get this input sentence, ABC. Then you have into your internal state the representation, the meaning of the sequence ABC. You use a special character, which is go or start of sequence, and you predict the first character. Once you have predicted the first character, you input to the network the very same character, and you predict the second, and so on, and so on. And this is what happens. At a certain point, your network will predict a special character, which is the end of sentence, which says, I have generated the output. There's a question on the chat. I was reading it. Can you repeat in many-to-many what is the advantage of the case on the left where we have more LSTM units? Just a second, let me understand your question. So in this case, it's a many-to-many, where what to do is you embed your question into a hidden representation, and then you base your question or your translation based on this hidden representation. In this case, when you have like one item depending immediately from the other, you have basically the many-to-many, but with no, let's say, this first embedding and then second embedding, and so you produce already the first output without having seen the future. In this case, you wait until the end of the sentence to predict the first character. Conceptually, this is the main difference. In many-to-many on the left, you have to wait all the characters because before predicting the first one. In the many-to-many, you can immediately start predicting. On the one on the left, obviously, you have a more informed prediction. The one on the right, you have less informed but faster because you don't have to see the entire sequence presented to the model before it can start directly. Okay, question. Can you repeat the difference between training and inference? Yes, let's go back here. So let's see if I have another slide to clarify this question. I should have it. Yeah, I will answer this in front of the next slide. So I'll keep your question for 5 minutes later. Okay. There's another question. So since the encoder has seen the whole sentence before doing prediction, is it equivalent to a bilateral or bidirectional LSTM network? Not really, because in this case, let me erase everything. Not really, because this embedding is the embedding that contains information only in one direction. while in the case of bidirectional, you kind of mix information also from the future when predicting the one in the middle. The bidirectional one, it's to be honest, is more used in the context which is reported on the right. So the typical use of a bidirectional one is this one. So you have, and this goes in this direction. And then you do it, you stack it. But there is a subtle difference, not a critical one. I mean, as usual, if you have many hypotheses that you cannot rule out by using theory, you have to set up an experimental campaign to figure out what is the right answer. Okay. To train this network, you need to prepare the data in a particular way. So why? Because you have to write the sentences which are the input here and the output of the network. So let me use the colors that are more or less they are in the slide. So this is the blue one is the output, the red one is the input, and this is one of the first things to prepare. And then you need to, let's say, add special characters. Let me use here lighter, it's easier to use. Like this one, which tells the machine when the input sentence is finished and when it is not. Now, as you have seen in the homework, the way you set up the training is by using batches or mini batches. Data in each batch or mini batch should have the same size. This is a requirement for an efficient computation. So what does it mean? It means that all the sentences in input to the network should have the same length. But you cannot force all the sentences or sequences to have the same length. So what you do, you take, I don't know, 10 sequences to be added to the batch, you take the longest one, and you extend the shortest by adding some padding. The padding is a filling element which we have seen already when talking about convolutions. I mean, is a set of zeros around the image to make it possible to perform full image convolutions. In this case, the padding is a fictitious element in the sequence, which we use to have all the sequences in the batch have the same length. Another character that we would like to add is the character which ends the prediction. Why? Because if the prediction in this case is wxyz, after z we want to stop generating characters, otherwise we will keep generating characters forever. So we need to learn that when we are at the end of the sentence, we should predict end of sentence. And this is how we supervised this, let's say, technical aspect. Sorry, we supervise this ending of the generative approach model. I will discuss this in the second part of today's lecture. But in order to input a sequence, maybe a sequence of letters, a sequence of numbers, a sequence of sentences, and so on, a sequence of words, you have to encode them. So you have you need to have an encoding or a representation for them. Now, if the letters are, in this case, A, B, C, are word, the number of possible letters depends on the vocabulary of your country or of your language. So it is quite big. So usually a, let's say, small data set is used, and when there is a word which does not show up in the vocabulary, what we do, we replace it when we have it in the input, but we replace it with an unknown symbol when we have it as an input, but we didn't train our network to learn that word, to use that word. Last but not least, as I said already, the start of sentence or go, which I used to move from the input sequence to the output sequence. Let's see if I have other questions. Okay, these I answered already. The next question that is there is about, oh yes, by the way, here I presented PAD, EOS, unknown, and Go SOS as special characters. Depending on the library, the model, or the tool you are using, these special characters might have different name. And an example is already at the end of this slide, where the start of sequence sometimes is also called Go, but this is a minor detail. How do you train this network? Well, we know we train them in batches. So basically, we prepare a batch of input-output pairs. The input is, for instance, as you see here, a sentence in French, le chat est noir, with a marker of the end of sentence. This sequence gets encoded. Encoding means to generate this internal state, and then this is decoded into a sentence, which is the cat is black, which is the translation of the first sequence. At training time, so you know already what is the sentence for translating. So at training time, you try to, let's say, translate this sequence into this sequence, and you do all the characters at the time. At the testing time, what you do, you predict the first character. Let me highlight this different. At the training time, you start with the context and the start of sentence, which is a special symbol. Your decoder says, given the context, the first word that I would use is the. So this is the first word that it's generated. This becomes the input of my network. This input, based on the current state, gives you cat here. Then you input cat as a third input in the sequence. You get black, and then you input, then black. Then you input these two, and eventually you will get an end of sentence which has generated this. So at training time, I just try to predict a shifted version of the throughout. Sorry, I'm just trying to predict the output given a shifted version of the output itself. When it comes to the inference, I mean, you don't have the output because you're trying to predict. But since you predict one item at a time, you use the predicted item as input for the next prediction. Okay, there is let's say there is another question. If we are padding all the inputs to have the same length, so why do we use Go? Well, we don't pad all the input to have the same length. We pad all the input in the batch to have the same length. So basically, the same sentence happening in different batches might have a different number of pads, and sequences might have a different length, depending on the longest sequence or sentence in the batch at that time. Other questions? Okay. So, prepare the batch, append the end of sentence, prepend the start of sentence to the output, and you get the sorry, where it is my sorry, no, I don't have erase everything. So you postpend here at the end of the sequence, you start here with the sequence, and then you put here the target sequence after the start of sequence for the input, and the target sequence followed by the end of sequence to the output. Then you might want to pad for the right length. By the way, thank you for asking, but I didn't give you a complete answer. The padding is added after the end of sequence. So basically, by the end of sequence, it means that you do not, let's say, consider padding as an input. That's another aspect I forgot to mention. What about the encoding? So the encoding is a very important part. I mean, it's the encoding is probably what has revolutionized the text classification, text processing. All modern text analysis has been, let's say, rewritten by the idea of embedding. Let me state this very simplistic now. Words are symbols, unique symbols. You would like to turn them in numbers, or better, in vectors. One possible way is to use a vocabulary, and then use a vector which is as long as the vocabulary with only one number, which is 1, where the word is present, or we use an embedding technique. The remaining part of today's lecture, after I've done with the sequence-to-sequence model, will be about how to generate word embedding. So this will become totally clear in an hour or two. Sometimes, as I mentioned, your sentence contains words which do not exist into the vocabulary, so you have to replace them with an unknown symbol. OOV in this case stands for out of vocabulary item. Okay. How is the loss computed in this case? Thank you for the question. Is described in this slide. So in this case, what I want to predict as a loss is the error in predicting each output. So what does it mean? Let's start with the set of pairs. S is the source sentence, T is the target sentence. So basically, for any source sentence, I will predict one T prime output sequence, which should be as close as possible to the desired target sequence. So, for instance, in a question answering task, you get, are you free tomorrow? Then you have the start. The desired answer is yes, what's up? And if this is your answer, the target answer should be yes, what's up? So basically, you can imagine the prediction problem as a classification problem during a sequence. So the first is, what is the item in the vocabulary that I should put out now? Yes. What is the item within the vocabulary that I should put now? What? What is the output in the vocabulary which I should put it out now? Up. So basically, you have a sequence of classification tasks. If we try to apply the idea of maximum likelihood, let's put it this way, to this problem, so we have the probability of the sequence y1, y2, yt for the length of the target given a certain length of the input, we can assume that given the previous words, each output is independent from all the others. So you can imagine that the likelihood of a sequence is, let me start from here, is the probability of yes, given that I gave you start, times the probability of what, given that I gave you yes, times the probability of up, given that I give you what, and the probability of end, given that the input was up. So basically you have actually four conditioned probabilities. So you have four classification tasks, and if you consider them conditionally independent, so what does it mean? Given that I already said yes, what is the probability of what? So because of this, you try to compute the, basically this is the entropy, it's the cross entropy. So this is the average cross entropy along the sequence. Why it is the cross entropy? Just a brief recall to the mathematics of cross entropy. So basically, if you remember, the cross entropy is the sum over all the data of the target times, transposed, times the logarithm of the, logarithm of, logarithm of the probability, the a posteriori probability of the target class given your input. This is the cross entropy. So basically, this is in practice the sum. This is either 1 or 0. This is the log probabilities for all the targets of the sequence. Okay, let me see the question. But if what is the output of yes, how can they be independent? Okay, indeed they are not independent, they are conditionally independent. So what does it mean? You assume that the probability of, you try to compute the probability of yes given start times the probability of what's my computer is kind of slowed down, but I should arrive, given yes. This is yes. So you consider the probability of the output, the probability of yes given starts times the probability of what given yes times the probability of this. They are not independent because actually the probability of what depends on yes. Is it some kind of perplexity measure for the language processing? Yes, it is kind of correct. What is, I don't see the question. What is V? Is it V? It is it V? I don't see V. Let me see if can you clarify what you mean by what is V in the probably it was yes, but it is a Markov chain, yes. It is a sort of Markov. So you assume that the text is a Markov chain. I will talk about this after when I will discuss about the language model. But yes, this is a simplified version of text. Oh, what is V? Oh, okay, you're right. Now, thank you very much. So first, shouldn't be a minimum. Yes, there should be a minimum. Where is my? Okay, sorry. There should be a minimum over here, and this should be maximized. Either you put the minus and you minimize, or you maximize. But it is a maximum likelihood approach. What is V? V is the current, you're right, it's not written in the state, it's the current hidden state. Hidden state. So the prediction of a word depends on the previous word and the hidden state. So that's what is V. Okay. Other questions, doubts? Okay. This idea of having the probability of a word depending on the previous word will come back in 15 minutes, half an hour. Don't worry. It is something that is used very often in text prediction or in text modeling as well. Okay, I hope I answered all the questions. I'm just skimming through the chat. If not, please propose a new question again. Now, this is, okay, to be honest, this was the state of the art in language modeling, in text prediction, in sequence-to-sequence modeling. Nowadays, this is the simplest ever model possible in sequence-to-sequence modeling. What I would like to discuss today is one very important aspect that will let us explore a little bit some notions that we just scratched during the course. That are, how do we encode these symbols? So how do we embed these words? And this is the concept of word embedding. And after that, I would like to discuss advanced models to perform this thing. Nowadays, this is the baseline. So you basically consider the sequence-to-sequence model as the baseline for sequence modeling. Nowadays, we have models which are more stratified. They use what is called the attention mechanism. And I will discuss these models later on next week. I see that someone is, let's say, asking why we assume this Markov property to hold. Does it really hold this property that we can consider the probability, joint probability of a text as the probability of one word given the previous time the previous given the previous, and so on? Please wait 15 minutes and I will give you an answer. More detailed, but I can already tell you that the answer is no. The Markov property does not hold. The problem is that if you try to model the full joint distribution of a text, is basically unfeasible. So this is a simplifying assumption that the probability of one word depends on the previous word plus the context of the sentence, but modeling the full joint distribution of words and sentences, it's basically impossible. Another question is the hidden, oh sorry, just a second. The hidden state V is dependent also on the output already produced, right? Or does it only depend on the input? No. The hidden state, which is this V, just a second, need pen. Let's try to do it dark. I have always problems in looking at it. So the hidden state, you see it here, depends on the previous output of the LSTM, but on top of the LSTM, to predict yes, you will probably need a softmax of or a second layer of LSTM. I mean, this is a basic problem. I mean, in principle, this sequence to sequence could be something like a stacked LSTM model. So you have a stack of LSTM, so you have a hierarchical model, and at that point you have, let me read, so this is the starting of the sequence, then you have the inner state, and the output of this stack after the softmax get into the in. So yes, there is already some information about the state over there, but usually this is important because you know what was the word that was just selected, and for instance you don't select it again, because the joint probability of selecting a word given that you have just generated that word is basically zero. Basically, not totally zero, but it's basically zero. Okay, other questions, doubts? Okay, now if you don't mind, usually the timing that I keep is I will have 1 hour and a half, the first half, and 1 hour scarce, the second half of the lecture. Today I would like to restrict the first part and have it longer, the second, to cut at the right time in terms of topic. So I will continue answer the question about this topic, and then I will make the break, also if it is not yet 6, because I think that the next topic would be nice to have treated all together without any break. But I have another question. So the hidden state of in the decoder are dependent on the hidden state of the input. but become independent once the hidden state in the output are known. No. Don't confuse your assumption that you make here about how to compute the likelihood of a sentence from the assumption which are in the model. The conditional independence in the model is the assumption you make to make an easy evaluation of the loss. It somehow has here in V some memory of all the previous states. So basically, what we do is we assume this to be true, but in a sense, the current, let's say, probability depends on this and on all the sequence, because the state depends on all the sequence. Okay. Can you repeat how the encoder computes the context? How it computes the context? See LSTM. This is an LSTM. The context is the state, is the C and H. So this is C at time t minus 1 and H at times minus 1 of the LSTM. So this context, which is this, let's say, orange block, is the result of the state of your LSTM after having received the entire sequence. There is a question on an LSTM where I discussed last time the fact that the vanishing gradient is solved by a ReLU. The vanishing gradient is solved by a ReLU in deep network, but in the LSTM is not a ReLU, is a linear function. And so this is, and it is the circular error causal. Exactly. So that's correct. And this is, if you can read it in the slide, but it's very small, is this plus. This plus is the circular linear causal, sorry, circular error causal. Okay, let's see if I have, I hope I have answered all the questions. Okay. Okay, hope so. I will come back on this idea of, as I promised, of a language model. So why we do this to compute the likelihood of a word after following another. It is a very classical way of representing and modeling a language. After the break, I will stop now. Just a second, I'm just double checking the question. I will stop now talking about, let's say, sequences for the next hour, and I will spend some time on word embedding, which is how do we encode words. I will come back on advanced models for sequence processing next week, when I will discuss advanced models for analyzing sequences. Don't worry, I will come back to this. But I think that so far this is the minimum you need to do two things. One is to do the exercising on long short-term memories and sequence modeling, and second, to understand the basic element of sequence generation, which is the right-hand side of this image, and the let's say sequence understanding, which is the left hand of this sequence. Let me spend 1 minute, since I talked about sequence generation. At this point, if you remove this part, here, and you replace it by, I don't know, one convolutional neural network, like BGG, so for instance, or, I mean, you develop your own deep neural network, and you take, then you do the flattening, and you get this vector, which is the flattening of, and you input this as an input vector for the state of long short-term memory. What you have done here, you have something which encodes images into a context, and something that generates text about that context. So basically, this is a captioning model. So generating text in order to describe an image. This is a captioning task. Last year we wanted to give you as a last homework a captioning exercise. It was not possible. The reason why it was not possible is because the evaluation of captioning within Kaggle was basically horrible. So we didn't have a way to let you do captioning on as an exercise. I think it's a very nice project which puts together images and text. We are studying a way to make it possible today, this year, as a possible homework. But I mean, writing a captioning system, a basic captioning system, is as easy as taking an image encoding like any VGG, cutting it out, adding, well, you have to figure out how to do it, but adding the output of this encoder as init of the state of an LSTM, and then start the coding based on this context, and you start with the captioning. So that was the idea that we wanted to exploit last year. The problem of last year was that we couldn't automate the evaluation of your results, so it was going to be too complex for you to submit the answer. But that would be a possible idea for today, this year activity. Okay, we should be done with all the questions, with all the doubts, and even some advanced topics. As usual, I will pause the recording now, and my idea is to have a 15 minutes break. It is 5:44 at my watch, so my suggestion is that we start again at 6, and we do the last part of the class, which is about word embedding, because this is a pre-requirement for the sequence-to-sequence learning that so far I have been somehow fuzzy on. Okay, see you at 6. Okay, I'm back. Let me share my screen. Okay, should appear. Okay. Okay, so welcome back. Going to restart the recording in a minute. Okay, in the previous part of today's lecture, I have talked about the model, which is known as the sequence-to-sequence model, and it is the base for sequence processing and, in general, sequence-to-sequence processing. The sequences that I'm thinking about are text most of the time, because long short-term memories have been proved to be very, very, very effective with text. But the model, which goes under the name of text-to-text, sequence-to-sequence, sorry, has been used also for time series prediction and, in general, for any sequence-to-sequence mapping task. Now, with time series, it is relatively simple to see how the input is encoded, because you have either a scalar value which changes during time, or you might have a vector, so a set of variables that you observed during time, and because of this, you have a sequence to be let's say, tracked. Now the question is, how do we input, or how do we treat the sequences of words? To do this, we have to encode words, and this is what is done nowadays with word embedding. Encoding words is not a new task. I mean, people have been encoding words since the first text were processed, since the first works with text classification and text mining. Indeed, we will start exactly from those models of text mining, so those models which are used for embedding words. Let's start before with another model, which I will need later on. It is a model that you should have already seen in one lecture with Giacomo Boracchi, so it should be not new to you, but in case, let me recall how it works and what it is used for. The model I'm talking about is the so-called autoencoder. Sorry, I don't know why this happens. Okay. So what is an autoencoder? Well, an autoencoder is a self-supervised model. So it is an unsupervised model where you have an input vector, which is x here, and you try to map this vector into a hidden representation, and then you map this hidden representation back to x prime, where x prime is the original vector x. So basically, on a first sight, what is done by an autoencoder is just to learn the identity function. So what I learn is a function where you get an input x, and as output you get the very same input. So apparently you see the identity function. Okay, what is different from the identity function? First of all, what you do usually is to put a limited number of hidden units. What does it mean? It means that your internal representation of x is a compressed representation. So what you do is to compress X into a representation H in such a way that when you reconstruct this representation, you are able to retain the most of information. So basically, it is a compression problem where you try to minimize the reconstruction error. The second aspect of neural autoencoders and autoencoders in general is that you try to make this representation sparse. What does it mean? It means that not only you want to use less neurons, but you want that most of those are zero. So first, compressed representation. Second, sparse representation. What does it mean? It means that if you have inputs which are clustered, you should have, in principle, one output which is different from zero, which represents that cluster of input, one output of the hidden neuron, which is one, which represents that cluster, and all the other to be zero. So this is a second constraint which allows to go beyond the basic identity function. I mean, this is a compressed, sparse representation of your input. Okay. You can think about the first part, and this is one of the key aspects of autoencoders, as an encoder, as the name suggests, and the second part as a decoding part. So basically, you have an input X, you encode the input in some hidden representation Hj, where J is the neuron in the hidden layer of X, which is based on the weight which is learned. So the problem becomes taking some data in an encoding space, in an original space, projecting this space, this data in a sort of embedding space, and then decoding this data in the original space, and you want that the embedding space should have a dimensionality which is lower than the original one. So this is a property that you would like to have, is that you start from a high dimensionality space and you project your data into a new space which has a lower dimensionality. So this is what the autoencoder does. Takes the data in one space, maps the data in a hidden space, and then reconstructs the data. To do this, you have to minimize the reconstruction error. What does it mean? It means that if the inner representation has captured all the information about the input, you should be able to reconstruct this data accurately. And the second term is a sort of sparsity term, where you try to push the inner representation into having a lot of zeros. So it's a regularization term. Question: why do I want the representation sparse? Because first of all, sparse terms are orthogonal terms. Because it is more likely that the sparse vectors are orthogonal each other. If they are orthogonal each other, it means that they represent different characteristics of the input, and they sort of represent orthogonal vectors, orthogonal bases, upon which the original data are reconstructed. So it is a regularization term to make the problem more, let's say, constrained, more regularized, and this sparsity term somehow tries to say, okay, if this one is 1 and the other are 0, it is like having one cluster of input represented by this neuron, and this cluster of input gets reconstructed when your data belongs or activate this cluster of, let's say, hidden neuron. So the reason to be sparse is to have an orthogonal base, almost orthogonal base. It is not enforced to be orthogonal, and to have, let's say, a further regularization, which is compressing even more. What I have you noticed is that the absolute value here is on the output of the neuron. So it is an L1 regularization, which, as you know, is a sparsifying loss applied to the output of the neurons, not to the weights. This is a peculiarity of the sparse neural autoencoder. Okay. Okay, this was the background. So let's keep this in mind as something you should know. What is an autoencoder, and how you training, and what it is used for. But now that we have recalled this part, let's go to the problem of word embedding. And to better understand, let's try to see how words are represented in machine learning. So usually words are represented as discrete atomic symbols. What does it mean? It means that the word cat is encoded as a unique symbol. The term dog is encoded by another unique symbol, and there is no whatsoever semantical content in these symbols. Usually, what are these symbols are the position of the word cat and the word dog in a dictionary. Indeed, one of the most used encoding for text is the one-hot encoding form. What does it mean? It means that if you have the word cat, which is the second item in a dictionary, well, the word cat becomes 0, 1, 0, 0, 0, and so on. This is the word cat in a dictionary. If you have the word dog and it happens to end in the one but the last of the dictionary, you will have a set of zeros, then 0, 1, 0. So this is the word dog. You see immediately one of the problem of this encoding, which is encoding are very, very, very long. Because a typical dictionary can be, I don't know, 300,000 words. I mean, it is even a small dictionary. So basically, to represent one symbol, you need a vector of 300,000 numbers, out of which only one is different from 0. And this is very different from what it is done in audio, where you have a very dense representation. And density means that you can build a distance metric in this space, and you have a sort of smoothness in this space. And the points in this space, since it is dense, they are very similar to themselves when they are very close to themselves. And the same holds for an image. So if you take an image and you remove some pixels like this one, sorry, like these ones. So if you make them black, you have not changed the sense of this image. I mean, it's a very small little piece of change. By the way, the number of pixels in this image is easily in the order of 300K. I mean, it's not that the problem is because I have more number or less number. No, the problem is because this representation is very, very sparse. You say, hey, but you say that you want a sparse representation. Yes, I want a sparse representation in a low dimensionality space, not a sparse representation in a huge dimensionality space. So basically what happens is that because this information is very sparse, there are a lot of issues, and the most common one is this problem, which is related to the use of the bag of word encoding. Now, for the people of you that have done either data mining or text mining or some text processing and classification, you probably know what is the bag of word. Bag of word means that you treat any word in an independent manner. And so basically what happens is that a text is encoded by a vector which is as long as the vocabulary, and it has a 1 if a certain word, the word corresponding to the word in the vocabulary, is present. And because of this, you have a vector of 0, 1, and 0, 1. There are improved encoding where you normalized by the frequency of that word, because having the word the in a document is not really relevant. If you have the word psychiatrics in a vector or in a text, then it becomes very relevant. And this is how you encode typically text via a bag of word encoding. As I said, the main problem of word encode, of one-hot encoding is due to the fact that the space is sparse, and most critically, it has a high dimensionality. It means that to estimate any probability distribution over this space, it takes an exponential memory, an exponential number of parameters, and an exponential time. So the proposal of solving this, let's say, encoding problem for text has shown different time in the literature, especially for encoding documents, because usually text analysis is about encoding documents, because then on those documents you want to basically base any document retrieval or classification algorithm. So how do you encode a document? How do you model text? This is a very serious issue. I mean, it's so serious because that it had finding a proper way of encoding text has changed the performances of chatbot, classifiers, information retrieval system, automatic translation system. The big change in any NLP task has started with finding a proper way of encoding text. In the history, bag of words was just one way of encoding text. I mean, we have already discussed bag of word encoding a minute ago. So you have a long vector where you store the let's say the one or a number which is a ratio between the frequency and the relative frequency of a word to represent a text. Another well-known model to represent text is the so-called n-gram models. I will discuss what it is these n-gram models in a minute. These are the so-called local representation. What does it mean? It means that you represent a document via local features. Local means close to the words. Bag of word represents this document by 1, 0, or a number related to the word. N-gram we will see in a minute. There is an alternative way, which is called continuous representation. In continuous representation, you move from a discrete approach, which is related to the words, and you move to a more continuous space representation. We will see that continuous representation have been introduced to overcome the limits of local representation. But let's start from the most known local representation. It dates back to the 80s, so it's a very, let's say, well-known modeling strategy. And it is about modeling the probability of one term given the terms that have been preceding this term. So let's assume you have a document. We would like to, or a sentence, it's the same thing. We would like to compute the probability of this sentence. Why we would like to understand the probability of a given sentence? Because let's assume that we want to perform some maximum a posteriori probability for a certain class of a document. Basically, maximum posteriori probability is the probability of the document given one class, the probability of the document given the other class, and then you select, well, you have to multiply by the a priori probability of the class, and then you select the one with the highest probability. So, understanding the probability, the joint probability of a sequence of words allows to understand basically what is the underlying model of a document. You can write this probability as this probability here. Notice that this is an exact expansion. So let me clarify this. The writing of, I need a more colorful pen. Here we go. So if I have the probability of, I don't know, 3 words, the joint probability of word 1, word 2, and word 3, I can use the chain rule, and I can say that this is equal to the probability of W1 times the probability of W, just a second, sorry, let me write it the other way around, which is easier to see the chain rule. Sorry, I can write it as the probability of W1 given W2 and W3 times 3 times the probability of W2 given W3 times the probability of W3. Notice that this is exact. It is an exact factorization. So basically, this exact representation is what is written here. The probability of a sequence is the product of the probability of a word given all the previous one, and so on and so forth. Okay, now to compute this probability, you need to compute the probability of one word given all the other words in the sequence, which is this one, times the second given all the others times this. Okay. How complex is to compute the probability of a word given all the others? This is very, very complex because we need to compute the probability of one word happening for any other combination of all the other variables. And you understand that computing this has an exponential complexity. Exponential complexity in the number of words. So basically, let's assume for a minute that I have a vocabulary of 10 words. This probability has 10 to the second possible values, because they are the values when we have the first word and the second, the first word and the third, the first word, and so on and so forth. So you have a complexity of the model which is exponential in how many words in the sequence. Question from this. Wasn't better the other way? How can W1 depends on W2? Oh, okay. It doesn't really matter. To be honest, this is exact as the other one. You can think about the reverse, but it's okay. Yes, you can consider. Indeed, here, where it is. Indeed, here in the model written here, you write it as the preceding word. It's okay. I mean, you're right. You're right. So, since having a history of words which is too big, usually what you do, you memorize only the previous n minus 1 word. This n minus 1 word goes under the term of n gram. An n-gram is a set of n words. One is this, and these are n minus 1. So this is the so-called n-gram model. So you can write this model by storing or learning the probability of any word giving all the n minus 1 word before it. And this is a model which comes from the 1987. This has a lot of problems, like if we try to have a 10-gram model, it means that you want to keep in mind 10 previous words. At the end, what happens is that you get, and you have 10,000 words, which is a relatively small number for a vocabulary. What you end up doing is to keep in memory a tensor which is 10,000 to the 10th. And you can understand that basically it is basically impossible to keep this in mind. Second, once you have this model which has 10,000 to the 10th possible values, you have to learn them. So how much data do you need to estimate all these numbers? And basically, you get this fact that most of these will be empty, not because the space is empty, just because you had not enough data to train this model. So also adding more data doesn't work, because the more data you add, the more unique words and the more this number explode. So the n-gram language model basically was developed in the 80s for corpuses. Corpus is a set of documents having 10 to the 6 words. This is the size of the vocabulary. But the most you could get was the 3-gram model. So the probability of W1 and 2 and 3 written as W3 given 1 and 2 times W2 given W1 times probability of W1 is the best model that was able to be written. And the reason is because this n-gram language model ideally will solve the problem of NLP or statistical NLP, but in practice doesn't work. Why I'm talking about this if it doesn't work? Because this problem is the origin of word embedding. Let's see what are the problems of the language model. First of all, if you try to model each word separately, it means that you miss the properties of synonymous or word similarity. If you just want to model, let's say, the correlation between words, you're still working with a one-hot encoding model. Then you have the conditional probability of one word given the others. But still, you are computing the one-hot encoding of the words, and then when you try to compare the word speak with the word address, what happens is that they are orthogonal, because they have no bit in common in the one-hot encoding. And the same happens for Obama and president. I keep Obama. I haven't decided yet which is the next president in the US right now. So, I mean, let's keep Obama. At least we are sure about that. And Illinois and Chicago, I mean, they should be somehow similar. But in the one-hot encoding, let's say, formula, which is basically the same encoding in the n-gram language model, you still have this word similarity ignorance, means that you ignore the similarity about the word. Okay. How to solve this? Well, to solve this, the idea that was proposed is the idea of taking these words in a, let's say, sparse space of, let's say, high dimensionality, transform this space in a, let's say, lower dense dimensionality space, and see if by doing this we could solve the n-gram language model. That was the idea behind the original embedding stuff. So what is an embedding? Well, an embedding is, at least in the concept of word embedding, is a technique that takes words which are sparse or phrase from a high dimensional space, which is the vocabulary with the one-hot encoding, and project this high dimensional vector into a lower dimensional numerical vector. You see the idea here? You take a vector from a high dimensional space, which is, by the way, sparse, and you project in a lower dimensional space. And you see here that this resembles a lot to the beginning of this lecture, where I presented the idea of the autoencoder or the embedding of an input. In the autoencoder, what we would like to do is to embed a word in such a way that we can reconstruct it. Here, what we would like is to have an embedding which preserve the fact that similar words should end up close to each other. So maybe food and beverages should go in this part of the space, relative should go in this part of the space, cities in this part of the space, and so on and so on. So we would like some embedding space where closeness is a sort of similarity, semantic similarity function. Okay. How to do that? Oh, sorry. No, this is no, that's the last slide. How to do this? So now we have all the pieces. We have the problem, which is the high dimensionality sparse representation of text. A possible solution, which could be the n-gram language model, but it is computational unfeasible. We have the solution provided by the dense embedding. How do we implement this? Okay, the idea is to represent this embedding by implementing what is called a distributed representation. What is a distributed representation? It means that you take a word W in vocabulary V. Typically, the vocabulary is pretty big, can get to 10 million words. You take this vocabulary in this high-dimensional sparse space, and you map it in a continuous m-dimensional space where m is usually a small number. So that's the idea of distributed representation, because in a number you can represent many words, because we have a sort of a continuous space where you're going to embed the other variables. So you have the word, you have a mapping in a lower dimensionality space. The word usually is represented as a one-hot encoding. Then you have another vector, which is represented as a real valued multi-dimensional vector. So this is the idea. You want to take a one-hot encoding, which has all the problems that we were seeing before, and we want to project this one-hot encoding into a continuous space, which has less dimension than the number of words. This will allow the, let's say, solution of this sparse problem by doing actually 3 actions. Compression, because you move from W to M. Smoothing, I told you that small changes in the encoding get abrupt changing in the word, while in continuous features, what you would like to have a smoothing, so a slow change in a word by change in this feature vector. And the densification, because instead of having a lot of word in a huge space, very rare and sparse in this space, you would like to have a dense set of points. Okay, so these are the ideas. The overall, let's say, goal is that similar words should end up to be close to each other in this feature space. This is a feature space, so basically the word Obama should end up close to the word president. Lots of goals, lots of ideas, very nice, but how do we actually implement? The idea came out in 2003. Well, actually, the first step to the idea came up in 2003 with what is called the neural net language model. So what was the goal of this model? So the goal of this model was to solve the n-gram problem. So what you would like to have is to have word t minus n, t minus n plus 1, t minus 2, t minus 1, with n as big as possible. And by taking this, what you would like to predict is the probability, or actually the most probable word, or the probability, given this input. So the idea of Benjo was to try to use a neural network to perform, to solve, to go beyond the n-gram model. So it is not yet a word embedding task. It is more a language modeling task. And he was thinking about this model. The model is doing this. It has an encoding matrix here, which encodes each one-hot word into a real valued vector. So this step here is our projection. And actually it does it for every word. So for this word, for this word, and for this word. So the idea of the neural net language model is to take the one-hot encoding, which is very huge because is n minus 1 times the size of the vocabulary, and project, this is the projection, into a lower space, which is n minus 1 times the size of the encoding. Then, by this classifier, the goal is to predict what is the most likely word given the previous one. Okay. The interesting thing is that this projection layer is what we would like to do, is to embed in a m-dimensional space our one-hot encoding vector. There was a very why it is so, because here you have the matrix C, which is this one, and this is m by the size of the vocabulary here. And when you have a vector which is a one-hot encoding, basically this one is selecting one specific part of this matrix. So basically in this line, in line 1, you have the encoding of word 1. And in line 2, you have the encoding of word 2 according to this. So basically this matrix is computing the projection of your one-hot encoding into an embedding space. Then you have a neural network, almost classic. You have a softmax output because you want the probability, the a posteriori probability of a word given this embedding, plus a multi-layer perceptron here between the, so this one is basically a multi-layer perceptron with an input layer which is given by the concatenation of your embeddings, a hidden layer here to process these embeddings, and then a softmax output. Very standard, I would like to say. What is the complexity? Well, you can compute the complexity by looking how many weights. Basically, the number of weights is given by this, in the sense that you have to compute n times m's, which is n the number of words, m the encoding of the words, and this is the complexity of the matrix, the projection matrix that I was discussing before. Then you have n times m times h, which is this dense layer here. This is the second element. And then you have another h times the size of the vocabulary, which is the basically the softmax, the dense layer to the softmax. So these are the things. Belgio show that this model was able to perform way better than the 3-gram model, which was the state of the art, and it was able to reach the level of 5-gram model or even 6-gram model. Remember that before that time it was not possible to go beyond 3. So it doubled the memory of the model. If you think that the complexity is exponential, I mean, it is a lot, this thing. The problem is that this model had a lot of parameters, so it could not be applied to corpus which were bigger than 14 million documents or so where it is here, or vocabulary with I don't know, 6k words or 100k words. So basically they started with 1.2 million words, 14 million words, but basically they couldn't scale too much. Still, way bigger than any result at that time, but basically it was so-so. There is a question. Earlier we said that we want a sparse representation in lower dimensional space, which is this one. But at the end, we obtain lower dimensionality and dense, which is this. Yes, that's correct. I mean, the concept of autoencoder was originally invented as a sparse autoencoder. In this case, the Benjo model, it's slightly different from the autoencoder, but the idea is the same. You see, you project in a lower dimensionality, and then in this dimensionality, you perform the. Can I interpret this projection as feature meaning extraction? Well, give me a time and I will answer your question, because this was the idea. Benjo and his group, they were very happy, but they didn't realize that they unintentionally invented the word2vec. Why unintentionally invented word2vec? Because word2vec was invented 10 years later based on this idea. So based on the neural net language model, which is this model that I was describing here, Mikolov and colleagues at Google, they wanted to apply this idea to bigger corpora, because Google had way more documents than the documents that were available to Benj in 2003. So Mikolov and others, they said, we need to reduce this model in order to be able to fit the model with bigger corpora. Watch out here, the training, it was in 20 years ago, but it takes 3 weeks of training to learn this model. Okay. Here it comes the idea of Mikolov and others. Now we know the basic point. We, based on the idea of projecting from one hot in a smaller, denser space, what we do is to learn a language model. Okay. The number of the complexity of the training, if you remember the number that I was showing before, is given by, let me recall this with you. The complexity is n by m plus, and this is the encoding. I mean, there is nothing you can do out of it. Then you have n times m times h, and this is the hidden layer part. And then you have h times the size of the vocabulary, and this is the softmax. Now, the encoding you cannot change because either you use less word or you use less smaller space. The output you cannot change. The idea was to remove the hidden layer. So if you remove the hidden layer, then you see that this term disappear, which is a very complex, let's say it's very computationally expensive term. And if you remove the learning rate, they were able to speed up this 1,000 times. Since you speed up 1,000 times, what you do is to be able to train on bigger data set. Plus, the projection layer is shared. What does it mean? I will come back to a minute to the idea of a shared projection layer. And then the next idea was to use as context not only the previous words but also the following words. So what does it mean? It means that instead of learning to predict the next word, they did something different. They removed one word and they tried to predict the missing word from the surrounding one. So it means that instead of, let's say, using text prediction, they did something like trying to predict this word, which is Neymar, by the word that surround it, like Pelé has scaled an excellent player, or occasionally as a attacking midfielder, Neymar was called the true phenomenon. So, as you see, and this is the key important part which answer the question, the last question that was asked on the chat. Can I think about this projection as the meaning, the feature of the word? Yes, and this projection is based on the surrounding. We will see it in a minute better, but basically what you want to do is to find a representation of the surrounding words, which is enough to predict this word, so that basically the encoding of this word is a sort of feature extraction of the text surrounding. And the idea is that this is an idea that comes from the 50s, that the meaning of a word is written in the word that surrounds it. To be honest, I'm not a really big soccer fan, and I didn't know that Pelé was named Neymar. I apologize with all the, let's say, soccer fan at this point. So, but by looking at the text around it, I understood what was this word. I recalled the meaning of the word. So the word is represented by the surround. So the model basically can be written in two ways. One is called skipgram, which is basically taking a word. Just a second, I need the highlighter. Taking a word, then applying the projection. So this is R to N, and it goes to R to M, which is small. And then from this projection, try to predict all the surrounding words. When you converge, basically this, let me remove the ink. So When you converge, this is the representation of this word because it encodes all the surrounding. And because the meaning of a word is given by the surrounding, basically you are able to find out semantic features. Let me make an example. What do you think it will be, the encoding of Neymar and the encoding of Pele? Well, based on this model, it will not be the same encoding, but it will be an encoding which will most likely be able to predict the same words. So it will be very, very similar. Let's do it the other way around. This is the so-called continuous bag of words, in which what you do is basically you take the one-hot encoding of the words around one term, you project and sum. This is the idea of, which was in the previous, in the previous slide, there was a projection layer is shared. It means that you project in this layer without concatenation, and this is the encoding which allows to predict the word. So basically, this encoding can be a surrogate of this word, and this encoding represents the word surrounding it. So basically, there is a semantic connection between these two. So think about two words, different words, which are surrounded by the same set of words. Most likely, they will mean the same thing. So the final model is this, which goes under the term of word-to-vec, or continuous bag of word. And what it does, it takes n minus 2 words before and n divided by 2 words before and divided by 2 words above. It projects with the lookup table everything and average that, and then tries by a softmax to predict what is the most likely missing word in the sentence. Well, there are some learning tricks which I will skip, but you can check if you want. These are more on the paper of Word2Vec. They are more on how to make these very fast. Let's see the complexity. You have the encoding, and then you have by this trick of speeding up the learning, you have an m time log of the vocabulary complexity. Very fast, they were able to train these with 6 billion words, with a vocabulary of 10 million words. The embedding was 1,000 numbers, sorry, 1,000 was 1,000 numbers. Yes, is the size of the embedding, and basically they were able to, let's say, capture more information, more context about the surrounding. Here I don't see how big was the n, but it was significantly bigger than the number of words given by Benjo. The nice thing is that in this space, distances of words are preserved. For instance, capitals and countries are at the same distance. So you have Athens at the same distance of Greece, and Rome as a capital of Italy, and so on and so forth. So basically, there are some vectors which are constant between tenses, superlatives, male, female, opposite. There's a question in the chat. Can you please repeat the main differences between the skip gram and the bag of work? That's yes, for sure. So the real difference, it's very simple. In the skip gram, no, I want to erase everything. In the skip gram, you take a word. Just a second, I need. So you take a word, which is this with a one-hot encoding. So this is, let's say, a vector 0, 0, 1, 0. You project into a vector which is 0.2, 0.5, and then you have a lot of model which simultaneously they try to predict all the words which are around the now I'm doing some encoding just to give you an idea, which are around that word. What does it mean? It means that you encode this word here into a representation which itself represents all these surroundings. So basically, this word is represented by a sort of average of the surrounding. The same thing is done here. The only thing is that instead of starting from the word you are interested in encoding, you start from its surrounding, you encode each of them and you compute the average of their encoding and you get your word. Basically what happens is that a word is represented by the average of their surrounding. Hope this answers your question. So the question is, so we learn how to predict the word given the context, correct? This preserve the distances for that similar word will give similar context. Yes, and vice versa. Similar context should result in similar words. Maybe not exactly the same, but I doubt that a word which is embedded in 50 words which are the same of another, they don't have the same meaning. Oh, this is the, I think, most interesting idea of the bag of word approach. Let me show you some results to conclude. There has been some very interesting visualization by taking this embedding space and looking which words are close to which. So it turns out that countries are very similar, are very close to one to the other. But what is interesting is that obviously also the capital of the country are very similar. And usually there is a constant distance between the capital of a country and its capital, because this distance should not be too big first. And basically this distance is constant because it is represented usually by the set of words which state Beijing is a marvelous city and it is the capital of China. Moscow is a marvelous city and it is the capital of Russia. Ankara is the capital, and so on. So you see that this difference is constant, and this is not enforced. It is discovered, and because of this, you can find other relationships. So, for instance, the relationship between male or female. So basically, princess and prince, queen and king, hero and hero. And the reason is because they will have the same words around with the same difference, which is the gender. Other nice examples are, if you take from king the set of words which represent a man, and you add the same of word which represent a woman, you should get a queen. And indeed, if you take the vector representing king, you remove the vector representing man, and you add the vector representing woman, you end up around queen. And the same can be done, like if you take Paris and you remove France, you add Italy, you get close to Rome. Or if you get Windows, you remove Microsoft, you add Google, you get Android. Don't think, well, you should think in terms of vectors, but vectors are the set of words in the context that represent that term. So if you take the Windows term and you remove from its context the set of words related to Microsoft, and you add the same set of words representing Google, what you get is an operating system built by Google. I mean, there's only Android over there. And there are other examples, like if you take Einstein and you remove the scientist and you get the painter, you get Picasso. Why? Because of the adjective, which are basically around the term, basically, and so on and so forth. I will not discuss all these examples, which are very nice and interesting, and I leave these for you in the slide. But when you think about word embedding, think about the context, because the key is the context, the regularities in the context, and these regularities represent the specific word by a linear, by a vector, a vector in the space. Some examples for information retrieval: you could add two vector and you see where you end up, because it means to add to context. If you add to context, you should add near a word which has those two contexts inside. And it doesn't work for long sentences, but for long sentences, you have the solution. You take all these words and you process these words via an LSTM. You build an embedding representation which represents the context. So now you see why the idea of word2vec, having taken words and having represented them in a space where distances represent semantic similarities, and similarity is computed in terms of average context which words have in common, has, let's say, changed the history of text processing. These are some other distances. So, for instance, you have Obama president has some distance in feature space, band president has another distance, concert media, concert and speech have other distance. And so basically, by computing which sentence on average is closer to another, you can compute the sentence similarity, for instance. And these are some other applications that I will skip. Two last sentences, then I will close today's lecture about word embedding in text. First of all, word2vec is the first embedding. Nowadays, there are many other embedding. One is called Globe, and basically what it does, it tries to, I will be faster, but don't worry, it is more a complex concept than something very, very technical. So instead of doing this indirectly, it tries to embed two words in such a way that the distance between these two words encodes the a posteriori probability between them. Basically, it learns directly what Word2Vec and learns indirectly. Again, this is another technique. I will not go into the detail. If you want, there is the Pennington and other paper, but that's it. If you're doubt, I will not ask you what is glove. I will stop my questions to Word2Vec. But I wanted to tell you that the Word2Vec is not the only word embedding technique. Actually, is the oldest one. Nowadays, there are more advanced techniques. They are based on the transformer architecture, but to understand those techniques, we need to understand the transformer architecture. The transformer architecture is the last topic of this course, so it will come next week when we will discuss advanced techniques for text processing. I'm not sure I will be able to finish all the topics in one lecture. Indeed, I think we have two lecture remaining. So next week, I will talk about attention mechanism, and the following week, I will talk about the transformer, which is also known as attention is all you need, because it is only based on attention. And this is another example on what happens if you embed the text with glove, and you see that if you search the 10 nearest words about frog, you find frog with a capital, frogs, plural, toad, which is another name of frog, Litoria, which is a specific kind of frog, as you see from the picture, Leptodactylide, which is another specific kind of frog, Rana, I don't know why they have it in Italian as well, Lizard, and Eleutherodactylus, which is this specific frog. There is lizard, which is not a frog, but it makes sense, because if you think in terms of the word, the text, what it means, the embedding, what it means, the embedding means the typical surrounding context of this word. And all these words, they share most of the context, and so probably they represent the same thing. Do this encoding gives you any idea about what is the thing that they represent? Not at all. The encoding just says that all these words represent the same context. If you are able to understand what the context means, then probably you are able to extract the meaning of this. So, for instance, I didn't know that Eleutherodactylus is a frog, but being around all this term, probably it is a frog. Okay, sorry for having rushed at the end, but I wanted to give you an overall view of word embedding, because it's a very, very, very important technique. I took it from a sort of long distance idea, which is the embedding of the embedding of vectors via autoencoder. The idea here is very similar. I would like you to appreciate at the end of the course that basically what happens is that most of deep learning is about learning a representation. And the deep learning can do this in a supervised and unsupervised way. Autoencoding and Word2Vec are two unsupervised way of learning and embedding. So this should be another take-home message of today. I see from a comment on the chat that Rana is actually a kind of frog. Thank you very much. I was clearly biased by being an Italian in this. Yes. Okay. I will stop the recording here. But if you have questions, I have. Oh yes, okay. Sorry, just there is a question now, which is a clarification. So the CW function is a table which map a word to its compressed vector representation whose values span a continuous space? Yes. Is this mapping function inferred via neural network? Okay, let's make it more simpler. So you can imagine this. Where is? Oh no, let me use another color which is more visible. Let's try this. So the idea is that you have your feature vector, and you compress it into another feature vector, right? So basically C, so let's say this is H and this is X. So basically X is equal C, sorry, H is equal to C times X. Here you can have plus bias, but this is, so the question is C a matrix? Yes. So can you implement it as a neural network? Yes. Basically it is a neural network which has no output value here. That's the point. It is a linear mapping. Can you have it non-linear? Yes, you can have it non-linear, but then it becomes more complex. There is a question. Has there been any work on the interpretability of the vector space of the words like there has been for CNN? Yes and no, in a sense that these plots, let me show some. These plots are more or less a sort of trying to interpret where words are mapped and what are the neighboring words. There are also some work which use the SNI, which is, I don't know if you have seen it with Boraki, is a visualization technique which gives you an idea of where words are. So basically, yes, there has been some work on interpretability in sense of visualization of the space and the clusters. If the question is the other way around, so because of which context two words are assumed to be the same, probably yes. I'm not aware, but I'm pretty sure there is. There is some interpretation of the attention mechanism. I will discuss this later on. By the way, the interpretability of these embeddings is relevant, but the interpretability of the other part, which is the sequence to sequence, is a key aspect. So I think that this is important. It is one embedding, understanding which words are which, and to understand what does it mean for two words to be similar. But I will come back a little bit about interpretability in the last lecture. Okay, thank you very much. I think I will stop here. It has been another long day for all of us, but we are getting close to the end of the course. As I mentioned, we will come up with the homework end of the week's beginning of the next, and you will have until the 18 more or less, or 22 13, and the last part of the third homework will be done during the holidays. Take the homework as an opportunity to experience with these tools and learn by doing. As I said, we don't grade the homework by the ranking, although we are very curious how you were able to reach such a high rank in some of the tasks. And it's very interesting that some of you even asked for the solution of the homework. Unfortunately, there is no solution. There are some techniques that have been used. If I manage to do that, I would like to have a sort of 10 minutes presentation by the best performing teams to share with the other what they did to win the homework. But this will be decided later on. I mean, we have still to understand a couple of things about this. Okay, thank you very much. See you, I think, next Thursday. I am not sure right now. I don't have my schedule in front of me. I can double check immediately on the course website, but we meet again next Thursday for one but the last lecture, unless it is a holiday or not. No, it shouldn't be a holiday, not at all. So we meet, we meet both on the 2nd and on the 3rd. I was not paying attention to this. Okay, thank you very much. Have a nice end of the week and weekend. Bye bye.